So I've rewritten 16x to the fourth as some quantity to the fourth power. So once I've done that, I can go ahead and just sort of cancel those out. And I have 2x. That is my simplified radical. Okay, so moving on. Let's go ahead here. So here we have the square root of 9x squared y to the fourth z to the sixth. So same idea. I'm going to go ahead and see if I can rewrite all of these as something to the, well, what is my radical? Oh, what number is sitting up here in the radical? Well, remember that's a 2. If we write it blank and you don't see the number, you're allowed to assume it's a 2. Okay, we want to write this as something to the second power. Let's see, can I write 9 as something to the second power? Well, 9 is 3 squared. So 3 squared. Okay, x to the second power. Well, that's the same, it's just x. How about y? What times itself twice gives me y to the fourth? Well, y squared. Y squared times y squared. Okay, so we'll go ahead and write y squared. And then lastly, we have z to the sixth. What times itself twice would give me z to the sixth power? Well, z to the third power. Z to the third, sorry, that's getting really small, times z to the third. And we'll go ahead and write that, z to the third. Now let's simplify. Okay, so I've written that all out, and I can go ahead and do that sort of canceling. And I'm left with 3xy squared z to the third power. And we're done with that one. Okay, so that concept of simplifying going on here and here, we're going to use in this next problem. So we're asked to perform the given operation and simplify. So what is the given operation? Well, addition. I'm being asked to add these two. But the problem is they're not like terms. I can't add them. So I'm going to go ahead and simplify and then see if I can add them. So let's look at this. This is a square root. So, can I rewrite 32 as something squared? Well, 32, what is that in exponential form anyways? 32 is 2 to the fifth power. And then we have x and y to the third power. Okay, now plus y, and let's see, can 8 be written as an exponent? Yeah, that's 2 to the third power, right? 2 times 2 times 2? Yeah, 2 to the third power. X, y. Okay, so let's see if we can simplify something in these radicals. Okay, so what we're going to do now is we're going to split this radical into the perfect square root numbers and the, you could call them imperfects. Okay. And then I'm going to copy this plus sign down right there. So looking at this radical, see that x? It's not going to be able to simplify because it only has a power to the 1. So we're going to write it down here. This guy doesn't get out. How about the y to the third power? Well, I need to have something squared. So I can rewrite y to the third power. Let me bring this up here. Y to the third power, I can rewrite that as y squared times 1. Sorry, y to the 1 power. So the y squared will get to go in the perfect squared side, and the leftover y will join the x on the imperfect side. Okay, so we've managed to split up the x and the y. Let's take a look at the 2. 2 to the fifth power is not a perfect square root. But what about, let's see, can I split 2 the same way I split up the y? 2 to the fifth power. Well, that is 2 to the fourth power times 2 to the first power. And 2 to the fourth power can be written as 2 squared times 2 to the 1 power. So I have just created a perfect square there. So 2 squared squared. And that leftover 2 is going to join these guys over here. Okay, so I've created the perfect squares. I had to sort of sort this through. Perfect squares in the first radical, and the leftovers are in the second radical. Okay, and I'm going to go ahead and do that to this side, the perfect radicals and the non-perfects. Go ahead and pause the video, see if you can split this by yourself. Alright, okay, so now let's take a look. 2 to the third power, that's not a perfect square root, so I'm going to split it. 2 to the third power is the same as 2 squared times 2. So this is the perfect square, and that's going to be the leftover part. So perfect square, leftover part. And then the x and y, oh, those guys aren't perfect squares. So they're going to go in the leftover part as well. Okay, so here we go. Let's rewrite this. So the perfect square parts, those are going to go ahead and cancel. And now they're out of the radical. They're free. Okay, 2 squared y. And this is all stuck in the radical still. And then we can simplify the 2 squared. So then we have y times 2, and then times 2xy. Let's clean this up a little bit. 2 squared is going to be 4y, square root of 2xy, plus 2y, square root of 2xy. Okay, so now we've simplified. We managed to simplify those radicals. Let's see, are these like terms? Can we add them? Well, let's take a look at the variable parts. This is the variable part, and this is the variable part. Are those two parts exactly the same? Well, let's see. Y, square root, 2xy, 2xy. Hey, they are like terms. So we have 2y squared of 2xy's plus 2y squared of 2xy's. So 4 plus 2 is going to give me 6y square root of 2xy's. Okay, and there we go. Okay, so first thing we did was simplify each of the radicals, and then we saw if they were like terms or not, so we could actually add them in the end. All right, we're chugging along. I think this is the last page for 1.2. Yep, and then it's your homework. All right, so rational exponents. All right, so here we go. If we have a to the fractional exponent m over n, we could rewrite it in 2 ways. One, we could do the radical inside raised to the m power, or we could do the m power inside and have the radical on the outside. And we have a condition that if n is an even number, then a is greater than or equal to 0. And that's the same condition that we had previously. Remember, so if we have the square root of 4, that's okay, but we can't have the square root of negative 4. Okay, so it's the same condition popping up right here. All right, so it says, answer in the form given unless stated otherwise. What does that mean? Well, that means if we're given an exponential version, answer in exponential unless told otherwise. If we're given radical, you can answer as a radical form unless stated otherwise. Okay, so let's go ahead and simplify this. 27 to the 2 over 3. Well, I have two options. One, I could focus on the denominator, the radical first, or I could focus on the power. I'm going to go ahead and split it into both of the options, two versions, this way or the other way, and then we'll talk about which way might be better. So let's try split it into the first form. This says take the bottom value, and that is your radical, and then raise it to your power. So the power would be 2. The other option we could do is we could do, first you raise it to the power, so the 2, and then you take the square root of it, or the cube root in this case. Okay, so there are 2 ways we could do this problem. And I'm going to do both of the ways, and then you can decide which one you think is simpler. Okay, So, starting with this way first, what's the cube root of 27? Well, that's 3. Okay, so that's simplified, and then we square it. And then, what is 3 squared? Well, that's 9. That wasn't too bad. So first we made it smaller, and then we made it bigger. Let's take a look at the other option. Oh, we've got a square 27. I have no idea what 27 squared is. Let me pull out my calculator. 27 times 27. 729. Oh, that is big. And now it's asking me to take the cube root of 729. I have no idea where to start there. I don't know what the cube root of 729 is. Actually, I do. It's going to be 9. So let's go ahead and check if that's right. So we're going to raise 729 to the half power, or the cube root power, 1 divided by 3. And what do we get? Hey, we get 9. Okay, so as you can see, both ways worked. The only thing is that most people prefer this method on the left side because you're making the numbers smaller, and we like to work with small numbers if can. Okay, your choice though. Both ways work. Okay, so let's go ahead and work on example 9. So it says to simplify. Okay, so this is all multiplication, so I'm just going to rewrite this in the multiplication. Okay. So we can multiply the two number parts together, 2 times 3. That'd be 6. Then times x times x. Now the problem here is we can't actually simplify these two in the form that they are in, because that's a square root and that's a fourth root. But I can figure out a way to simplify them if I translate to an exponent. So let's do that. Let's translate to an exponent. This is going to be x to the, well, remember that's a 2 down there, so this is going to be 1 over 2 power. Times, translating this, the fourth root, we'd get 1 to the 4th power. Now look at this. We can keep the base and add the exponents. So that's going to be 6 times x to the 2 plus 1 over 4. And now we're adding fractions. How do we add fractions? Well, they need to have the same denominator. So let's do the building up property and make this into a 4. That's going to be 6 times x to the 2 over 4 plus 1 over 4, which is going to be 6 times x to the 3 over 4. Okay. Now the problem here is that the given form was radical, but my answer is currently an exponential. So I'm going to go ahead and switch back to the radical form because that's what I was given. So switching back to the radical form, that's going to be, let's see, the bottom number is the radical. So that's going to be fourth root. And the top number is the power. So there we go. We have answered in the radical form because it was given in radical form. All right, last problem. Here we go. So we're going to rationalize denominators. Okay, so simplifying radicals. One thing first, we should not have fractions under a radical sign. So taking a look at example A, that's a no-no. There should be no perfect squares or cubes under the radical sign. So if you could simplify, you should. Here's an example. If you saw the square root of 4, you will not leave it that way. We will change it into 2. And the last part, no radical in the denominator of a fraction. Okay, so that's the rule we're going to go with. So if you had, for example, 1 over the square root of 2, we're not going to use that. We cannot leave a radical in the denominator, so we'd have to rationalize it. And we'll go over how to do that. All right, so part A. Well, right off the bat, I have a fraction under the radical, so I can't do that. So I'll go ahead and simplify this by splitting the radical into the top and the bottom. And from that, do we know what the square root of 1 is? Well, yeah, it's 1. And then what is the square root of 7? Well, I don't know what that is, so I'm just going to leave it as the square root of 7. But now I have a problem. I have a radical in the denominator. So what I need to do is I need to rationalize it. So I'm going to be sneaky. I'm going to multiply my denominator by another square root so that I end up with 7 squared in the bottom, and then I can cancel. So the question is, what do I multiply 7 by to get 7 squared? Well, 7. Okay, but once I multiply the bottom by something, I need to multiply the top by it. Remember, building up rule. Okay, so let's see. We have 1 times the square root of 7. Let's go ahead and write that in. And then we had the square root of 7 times the square root of 7, hey, which gave me the square root of 7 squared. And then I see that squared and the squared there, or the square root and the squared. I can go ahead and cancel those. And I'm left with square root of 7 over 7. I've rationalized my denominator. And we're done. Part B. Let's see. So we don't have any fractions under radical signs. We're good in that sense. But how about any perfect squares under radical signs? I see the square root of 4 going on there, so we're going to simplify that. The square root of 4 is 2. Okay, so we got that one out of the way. Now what's left? We need to rationalize the denominator. Okay, we can't have a radical in the denominator. Okay, so same plan as last time. This time it's a teeny bit different though, because we're using a cube root instead of a square root. So my goal is to get a perfect cube in the denominator. I need to multiply the bottom by something that can turn these into perfect cubes. Well, at the moment, this is a 2 to the 1 power. So I want to multiply by 2 to the, well, how many times would I need to multiply it by 2 to get 2 to the 3rd power? Twice. Because if we kept the base and added the exponents, we would get 2 to the 3rd power. Okay, so now we need to figure out how to make x squared into a perfect cube. Well, let's multiply by x to the 1 power. Okay, and then remember building up rule, gotta go ahead and multiply that to the top as well. Okay, so multiplying across the top, I have 2 cube root of 4x. And in the bottom, so keeping the radical, and then 2 to the 1st power times 2 to the 2nd power gives me 2 to the 3rd power. Then x squared times x to the 1st power gives me x to the 3rd power. All right, and once I've done that, I've now created the perfect cubes under the cube root. So we can go ahead and simplify. And I'm left with right there. You might be tempted to say we're done, but there's one thing left to do. Try to take a look. See those 2's? Those 2's are being multiplied, which means I can simplify them. So we'll go ahead and simplify out the 2's. And then I am left with the cube root of 4x over x. Let's see, do we have any fractions and radicals? No. Do we have any perfect cubes inside here? No. Do we have a radical in the denominator? Nope, all good. Okay, we're done. All right, so that was page 3 for 1.2. And then there is your homework page. Okay, go ahead and finish that up and turn that in by the end of the week. Email me if you have any questions.